Hello, everybody. This is Stefan. I'm currently a postdoc at the University of Copenhagen. So in this talk, I will be presenting the work that I've been doing in the past few years regarding enhancing object selection and manipulation for complex VR interaction. So before we actually talk about the details, let me quickly introduce myself. I started my journey as a research assistant during my undergraduate in Xi'an Jiaotong Liverpool University. I was attracted by the VR technology, as you can see from the video here, that I was really excited about it. And I started doing some research related to, for example, text entry and object selection in virtual reality. And after that, after taking a year gap, I started my PhD at Melbourne University. Here is a picture view of seeing from our office to the CBD region of Melbourne, which is quite nice. So my PhD topics also mainly focusing on selection and manipulation techniques in VR. And currently I'm in Copenhagen University in Denmark, starting my postdoc. And in this talk, I will be mainly talking about the work that I've been doing during the undergraduate research assistant period, and also the PhD student period. So let's get straight into it. So we humans have been exchanging information across time and space through, for example, pen and papers, smartphones, tablets, and PCs. It's normally the viewer stands or sits here watching the information over there. But VR, however, represents a complete paradigm shift. It is the first time that we are allowed to step into the virtual content, experiencing the digital world around us, where information is incarnated as virtual objects. So this VR technology is not only a sanctuary for people like me to escape from the physical reality, but it also changes how we perceive and interact with information, thus impacting the ways of communication, entertainment, and learning and creation. This paradigm shift also brings new challenges. For example, we find our existing input method based on keyboard and mouse and pens and pencils may not be suitable or applicable for this new virtual environment. And we probably need to explore new type method that can allow us to interact with the virtual object in the digital reality. Specifically, we want to know how can we be able to identify a targeted interest through object selection, and how can we coordinate the world around us through object manipulation. So existing techniques in virtual reality are mainly based on we call the mid-air selection and manipulation techniques. They have, for example, the virtual hand techniques where you are allowed to create a replica of your physical hand in a virtual environment so that you can be able to grab and translate the object around the world. They also have a technique called ray casting, where the ray is emanated from your hand position into the world so that you can use that ray to point at the object or even translate an object around the environment. So these media-based selection and manipulation techniques are very intuitive. They are very simple to use. However, there are several limitations as identified by the previous literature. For example, they will find to be slow and imprecise. They are inefficient. If you've heard of the Heisenberg effect, where when you point or position your object in midair, when you try to click the trigger to try to select an object by using the trigger action, your original position or orientation, your direction of your ray might be moved because of that trigger action. So this may lead to the misselection of your original intention, misselection of the target with this Heisenberg effect. They were also found to be fatiguing and cumbersome. We all probably heard about the gorilla arm effect when the user is like waving the arm in the midair for a long time, their arm will be fatiguing, right? Extremely fatiguing. They also sort of lack have limited functionalities, lack expressivity, which means that if we simply replicate how we do things in a physical reality, it might be a bit boring for the virtual world because we can actually leverage a lot of things to achieve more capabilities than what we can do in the physical world. So because of their limitation related to efficiency, ergonomics, and expressivity, this type of media selection and manipulation techniques, specifically the ray casting and virtual hand techniques, may not be suitable for more complex VR interaction scenarios. For example, we have scenarios that contain small, far away, occluded, or even dynamic targets, like this immersive analytics scenario, when the user wants to interact with, for example, several data points in the environment. How can they actually acquire this project data points and be able to select and manipulate them for further investigation? There are also scenario or tasks that require precise, versatile, or prolonged operations, like this 3D modeling scenario where the user's goal is sort of to create a large piece of artwork by translating the object into a correct position. So in this type of huge works, it is normally required that the user will have to work on that project for a long time, and you need to enable a lot of functionalities for the users to use. And sometimes it requires very precise position of the object, right? So in these complex VR interaction scenarios, the existing techniques might not be very useful in this case. So in order to try to tackle this problem, my overall research question of my past research is about how to improve the efficiency, ergonomics, and expressivity of media selection and manipulation techniques in more complex VR scenarios. Specifically, I focus on two types of research directions. One is we try to use the implicit assistance by using, for example, the predictive models and algorithms to try to automate the interaction process for the user, so that we can be able to, automate some of the process for users, so that with that automation, we can be able to, for example, improve their efficiency, or also lower their workload by using automated computing systems. Well, simply rely on the implicit assistant might not be enough, because we know sometimes the predictive models may not work. And what if our trusted AI agents betrayed us, right? In this sense, we also want to enable the explicit assistant, where we try to develop techniques that try to expand the user capability in manually achieving the desired interaction. So around these two research directions, I'll be talking about several projects that I've done in the past to more clearly illustrate my perspectives and how, with this implicit and explicit assistance, we can be able to support new type of VR interaction. So first, let's talk about the implicit assistant. So probably you've already inferred that in order to enable this kind of implicit assistance, we need some predictive models that can predict the user's intention, predict what they want to do, so that we can do the automation, right? So the most important thing is probably we have the accurate predictive model that can be able to help us to predict our intention. So the first project is related to how we actually build such a predictive models to predict users' selection behavior. In this project, we sort of consider a model to predict where the user typically performs a selection, giving a target in the environment. For example, when the user is trying to repetitively select an object, by performing this repetitive movement, you can see there is a sort of distribution formed inside a virtual environment, giving a particular target. So with this repetitive movements, we will see a distribution, which is the effective target, giving a nominal target, which represents a visual target that is shown to the user, right? As you can see from this picture, the effective target might not always be the same as the nominal target for the user selection. So in this work, we try to predict what's the effective target that the users will be able to, actually select that target by considering the features of the nominal target, which is a visual target. And in the first experiment, we try to see how target distance and object size may influence the user selection distribution, may influence the effective target. And in the second study, we try to extend all the parameters in a larger parameter ranges and try to incorporate the object depth factor in a 3D environment, because the virtual world is like in a 3D. So in this, with these two experiments, we are able to develop models that can predict based on a given target, its size, its distance, and its depth, and predict where the user will typically perform a selection given that target. And this can be applied to multiple applications. For example, when we try to predict the user selection time with Fitts law, we can be able to infer or we can be able to correct the real target that the user is actually targeting, giving the visual target, so that we can be able to better correct the Fitts law in some sense in order to offer a more accurate selection prediction, because the user's actual selection targets might not always be the same as the visual target. We also can use this model to predict the user selection accuracy by taking an integral on the selection distribution related to how the target is positioned related to the distribution, and we can be able to estimate the user selection accuracy. Additionally, we can also be able to use this selection distribution, this predicted distribution, to provide techniques to enable selection facilitation. For example, we can be able to automatically select the highest probable target given the user looking direction or pointing direction, so that we can be able to infer what object the user is trying to select with these probability distributions given by our model. As we can see from a very small experiment that we demonstrated that our model-based assistance will be able to offer significantly faster selection time and also much lower accuracy in these conditions. So recently we've tried to extend this endpoint distributions that we call into like other scenarios as well. For example, we consider how can we actually predict a temporal target, which is sort of travel along the line, and the user will only be able to select that target within a very limited time window after seeing the action of the target for a few times. And also we try to incorporate additional modality. For example, we use both eye gaze and head information as both the information to form that distribution, so that we can be, for example, more accurately infer the user's action. So with these prediction models, we can actually be able to predict the user selection behavior or predict their selection distribution given the targets in the environment. And now the second step we want to do is to take a more human-centric perspective by trying to consider how we can actually optimize the support for these predictive models so that we can be able to optimize the actual user performance. Yes, so the goal of this new project is to think about how can we actually optimize the support for a given predictive model to offer the optimal support for the user. In this project, we consider a technique called intelligent suggestion, which means that the target that can be able to predict the potential targets to the users and enable users to interact with these suggested targets through very easy to use a method such as a simple click. For example, we see without an intelligent suggestion, when the user is trying to select an object in the environment, the user might want to do the full range movement towards the object. And then if the object is sort of cluttered, the target is sort of cluttered, then the user needs to, precisely pointing at the object that they want to select. However, if we have an intelligent suggestion, we can be able to show the potential targets to the user by using, for example, like a pop-up notification, so that users will be able to see what's the likely object, if it is the object that they want to select, so that they can simply press a button and to interact with that object directly without actually doing all of this manual pointing. So let's try to organize our discussions again. Suppose that we have a prediction model that's trying to actively predict users' selection probability of all the objects inside an environment in a particular timing. And then when the user moves a little bit more, the prediction model will be able to update its confidence over time, right? Because by gathering more information from the user behavior, like their pointing behavior or their cursor position, the model will be able to be more confident gradually until the user is reaching the end, right? So once the probability distribution is updated, if the model is confident enough, if we want to provide a mechanism, then we can say, okay, are you trying to select, in this case, this WhatsApp icon in the environment, so that users don't have to point at the object. They can simply press the button B to interact with that object directly. So this sounds very promising. We can be able to automate some of the process for the user so that they don't have to do all of this manual pointing, which is, well, quite cumbersome, right? So there are also a lot of challenges related to this prediction. Of course, we need a very accurate target prediction model. We also need to consider when should we provide this suggestion. So our project actually aims to understand when to provide such suggestion. If we provide an early suggestion, the model may not be very confident because it haven't gathered a lot of user evidence. In this case, it might be able to provide a wrong suggestion, right? If the suggestion is wrong, it may delay the user's action and lead to like bad consequences. But if it is a correct suggestion with an early suggestion, then this suggestion will, of course, be able to save a lot of users' time in this case, right? What if we provide a later suggestion? If it is a later suggestion, the model will, of course, be more confident because it gathers more information about the user's movement. However, a later suggestion, the user might not be able to use that suggestion anymore because they almost complete their task. So what's the point of showing this later suggestion in this case? It will only be able to save a small amount of users' time. So in this case, we probably need an optimization strategy that can be able to help us to deal with this trade-off. So in this work, we try to propose a framework called COBO, the cost-benefit optimization framework, in order to help us to solve this optimal suggestion timing problem. Suppose that we have a target prediction model at hand. The first step of the framework is to do cost and benefit quantification. For example, if it is a correct suggestion, how much time that correct suggestion will be able to save for the user. And if it is an incorrect suggestion, how much time delay it will cause the user, and what's the user's likelihood of using a particular suggestion. And after we gather all of these evidence about this benefit and cost value, we can time or multiply all of that information to the correct and incorrect probability of user making of the model making a prediction, so that we can get a cost and benefit function. By using the benefit minus the cost function, we can actually get a gain function, which intuitively shows us when it is the beneficial point of showing any intelligent suggestion, because the gain is larger than 0. And we can also see what's the optimal timing of showing that suggestion based on this gain function, right? So with this, we conclude with our COBO framework. So in order to validate this framework, we first try to conduct a study on collecting data on users' behavior about how they react to the suggestions showing at different timing for different task scenarios. For example, we consider 2 task scenarios. One is small target selection. Your goal is to select a very small target located within the central of all of other distractors. We also have the task matching scenario, right? Text matching scenario, where the user's goal is to try to find the text in a list of potential candidates. We also have 2 suggestion types. One is the highlighting suggestion. It is incentral, it's less intrusive, and also we have like a more prompt, like a prompt for the user a pop-up notification in this case, right? And then in the second study, we try to, after gathering evidence about the user's behavior and how they react to different suggestion types at different timing, showing at different timing, we will be able to simulate the user's behavior and try to optimize our strategies like reinforcement learning agents to try to provide an optimal suggestion timing based on the simulated user behavior. And then in the third study, we try to deploy our agents and also the optimization framework into the real process to see whether our method will be able to provide useful help for the user. So from the results, we can see our COBO-based optimization actually lead to shorter task completion time and also higher usage percentage for the intelligent suggestion, which means that the users are more willing to use this kind of intelligent suggestions so that they don't have to do the manual pointing in this case. So this is for the text matching scenario. So this result sounds promising. And we can see by using the prediction model that try to infer the user's intended selection target, intended target of selection, and also combining with the optimal framework that try to provide an optimal support for the user, we can be able to save the user's time, improve their selection performance, and also lower their workload so that they don't have to manually point at the object or manually searching for the targets in the environment. So as we mentioned previously, the intelligent support, the implicit support might not always be beneficial because, for example, we don't have data for getting all of this user behavior, or in other cases, the intelligent support might not always be possible. So in this case, we want to add the explicit support so that users can be able to manually achieve the intended task by themselves. So here I also want to introduce two projects related to explicit assistant that we provide to the user. The first one is related to how we can be able to select a fully occluded object in the environment, in a virtual environment with occlusion visualization techniques. So the challenge of interacting with fully occluded target is quite prevalent in virtual environment. For example, when the user is in a 3D modeling scenario, the user wants to access an object that is hidden behind other structural elements like walls in this case. So it is very difficult to access that from a distant point of view because you can't see the target, and you probably need to teleport into different locations so that it's sort of cumbersome in this case. In another scenario, there are high-dimensional visualizations where the users probably try to find some of the target that is hidden behind other elements in these visualizations, so that it is very difficult to access this type of information if it is hidden behind. So existing techniques based on selection ray and also the ray casting and also the virtual hand offer very limited support for selecting fully occluded targets, even if this type of target selection might be able to help users a lot in different task scenarios. So in this work, we try to design different techniques that can be able to help the users to encounter these fully occluded target scenarios. For example, we consider using different occlusion visualizations, like we create a replica of the whole environment in front of the user, or we try to use the transparency, control the transparency of the object in the environment so that users can be able to reveal an object that is hidden behind. Or we try to use some volumetric probes, which means that we want to transfer the object into different locations so that the users can be able to identify the object easily. We also vary different design dimensions, for example, like different regions of interest. How can we specify what's the interesting region for the user, and how can we use different selection techniques for different techniques? And with this set of 7 techniques, we try to conduct the initial exploration and in a complex and also simple scenario to see their effect. And then we try to improve these 7 selection techniques. For example, we have derived one technique called gravity zone, where all the object is sort of absorbed to the location of the user. And if the distance between the object, the target, and the user is smaller than a certain distance, the object will disappear. So it's basically moving the object towards the user so that users can be able to identify the object that is hidden behind. We also have this lasso grid where the users can actually draw a trace in the environment, so all of the object in the environment will be projected onto a 2D grid, which is shown to be efficient for the users to select an object, right? So that users can identify all of the objects that are hidden behind by simply drawing a lasso trace. We also have a technique called the magic ball, where we create a transparent, well, semi-transparent mini-map in front of the user so that user can be able to see the environment from different perspectives, identify their target, and if they want to do a more accurate selection, they can arrange all of the objects onto a grid so that they can be able to, interact or see their target directly. They can also be able to interact with object directly on the mini-map as well. So with this, we try to conduct the second evaluation study. We consider different environment settings, like different layers of occlusions, what is depth of the target, how many number of target that we have in the environment, number of objects. And for example, we find that grid-based techniques is relatively more efficient and robust under different experimental conditions. So with these fully-occluded target selection techniques, we can be able to reveal a target that is hidden behind all of these walls and to interact with the target directly in this 3D modeling scenario. Okay, and we can also use this for sea exploration so that users can be able to see the hidden creatures behind the corals by drawing a lasso in the environment. In this case, the user draws a trace and then try to explore further about an animal called squid. And yeah, so as you can see with these fully-occluded selection techniques, we can be able to provide helpful support to allow users to achieve like imaginary techniques that they can't achieve in a physical environment, as well as improve their efficiency as compared to like teleport into that position and do some manipulation and teleport back, right? Apart from that, the fully-occluded target selection techniques, we try to explore how can we use like a lower level support, like by using different input modalities to provide the support for the user. We know that the modality based on like media selection is sort of cumbersome, and how can we incorporate other modalities like by using eye gaze, which is quick and rapid. Can we be able to like provide additional support based on incorporation of these new modalities? So specifically, we consider 2 new modalities. One is the eye gaze, because they are fast and lightweight, because the user, the eye gaze often indicates the intention of the user. User normally looks at the position first and then followed by the hand movement, right? So eye gaze, is that will that be able to help the user? We also consider another scenario called body surface, another modality. So because the body surface is always available, you normally carry your body around you when you're traveling around the virtual environment. And you can easily point to different position of your body with the eyes pre-targeting. And also it provides additional tactile feedback if you provide like gestures like this. And it can act as a supporting surface so that the media interaction is like probably not that cumbersome in this case, because you have a supporting surface. On the other hand, we also consider that these new modalities, the eye gaze and the body surfaces, cannot fully replace what we currently have in media interaction, because As you can see, you can move simply for the hand to move an object in the depth dimension in different dimensions, right? But with eye gaze, it's very difficult to estimate the depth that you are looking at. So it's very difficult to do the depth transformation or translation. Also, the body surface is mostly like a 2D surface, right? If you try to do some swipes and other interactions, it's mostly a 2D surface. So it cannot be able to fully support, or it is very cumbersome, or it is very hard to achieve this kind of 3D interaction based on this eye gaze and body surface. So our idea is to use this eye gaze and body surface as a supporting mechanism, as a complement method for the current method based on media interaction, right? So the question here will be, how can we actually incorporate this eye gaze and body surfaces into the existing workflow, which is already established based on this media interaction? How can we add this new modalities into the whole process? So in the gaze-supported mechanism or manipulation, we try to explore a design space on how gaze should be incorporated or should be combined with the hand inputs for virtual reality object manipulation. For example, we consider different design dimensions related to how gaze should be integrated into the whole process. It is only hand only, or it's hand plus gaze for object manipulation. We also consider how gaze and hand can coordinate with each other by considering, for example, whether when the selection is triggered, whether the object will be flying into the gaze position, the hand position, or staying in the gaze position. We also consider, for example, how gaze and hand can be able to transit between the two modalities so that we can easily input as we want. We can easily leverage whichever mechanism that we want to use with the techniques. For example, we consider the explicit transition where the user will be able to select an object with eye gaze and then look into another direction and then move the hand a little bit so that it's an explicit command that's telling the computer saying, okay, I'm now trying to switch from the eye gaze to the hand input so that we can be able to manipulate the hand by using our hand. So it's basically a transition from eye gaze to the hand in this case. We also consider another scenario where we try to use the program or use some mechanisms to determine which input modality is either the eye gaze or the hand that we are currently using. We here introduce a mechanism called the dynamic safe region. If the gaze point is sort of within this safe region, the gaze won't have an effect on the object, while if it is the gaze, it's like outside of this safe region, then the object will follow the gaze pointing direction. At the same time, the hand will be able to always control the object to a certain degree. So the object location is sort of one-to-one mapped into the hand movement as well. And in the body surface supported interaction, we try to also outline a design space on how on-body interfaces should be blended with the media interfaces. For example, we consider by using different input, the on-body input, body context information like touches, gestures, and deformations. We also consider media as information like the hand translation, rotation, and relationship between the two hands to provide an input. At the same time, we can also leverage the bimanual property of the hand to perform one hand the on-body input, the other hand the media input. We also consider the on-body surface and also the media input as the output. So by mapping these inputs into different output, we can draw different possibilities that haven't been explored in the literature about how can we combine the on-body and media for the input, how can we use the media input for on-body display manipulation, and how can we transition between the on-body content into our media content. Let me just show a few demonstrations. In this case, the user is using one of the hand to perform on-body gestures, and the other hand is performing the media gesture. As you can see in this scenario, the users can quickly switch between different colors by using the on-body gestures, specifically thumb to finger gestures, while drawing on the media, right? We don't have to disturb the main workflow of the media technique. In this case, the user wants to combine the on-body and the media relationship information between the two hands. While they are performing the on-body gestures, they can be able to switch between different on-body gestures so that the users can be able to rotate an object around the other or move the object towards the other, towards or away from each other, right? In another scenario, we try to use the finger on arm gestures so that users can be able to point at the particular direction using the hand gestures so that they can perform the follow-up gestures, the on-body gesture to reveal a fully occluded target. They may also use the similar strategy using the media position information plus the on-body gesture to select multiple objects in the environment. In this case, the user can be able to translate the object along 1 degree of freedom by using the media pointing gesture as well as the finger on arm gestures. In another example scenario, we can be able to translate the object in the media space into our body space so that when the user will teleport into different position, they can be able to get the object from their body. It's basically by using the body as the container for the users to place in or of the object. So this is sort of considering how can we combine the on-body gestures and also the media gestures or media input and output in order to offer better interaction, right? We can be able to control the object more precisely with, for example, 1 degree of freedom translation. We can also be able to, enable a lot of more functionality, additional functionalities for the user without using a menu placed in the media, right? Users can easily use, for example, the eyes-free text, the eyes-free entry for selecting different mechanisms. So from the study results, we find the eye gaze will be able to reduce fatigue, of course. They also are good for like distant object manipulation because eyes can easily looking into a direction, and then you can follow up by the hand input for more precise control. We also find the body surface will be able to offer quick access to different tools. The user can use the body as a container and can use different icons placed on the body to quickly switch between different functionalities, which sort of enable more complex interaction. Another relevant thoughts related to by using additional modalities is that we need to be careful about like switching between different modalities or using different modalities might add cognitive loads to the user, so that we need to be cautious about like applying this kind of multimodality method for the future. But in summary, our explicit support based on occlusion visualization techniques, the additional modality, including eye gaze and body surface, will be able to improve the user's performance and also lower their workload. They don't have to, performing these cumbersome media gestures. And then this type of techniques offer new additional support for VR interaction. So in summary, we try to use this explicit and implicit method to try to assist the user in a more usable and useful VR experience. And we believe that by adding, for example, the automation for the user and also adding additional support for the users to manually interact with the object, to manually achieve their tasks will be helpful in the future. And thanks for listening.